All right, let's dive into something that sounds almost like magic. We're talking about how we can take the toughest materials on Earth and shape them into incredibly precise parts. Things for jet engines or even surgical implants. This is all about the factors affecting machinability.
So, how on earth do you do it? I mean, seriously, think about it. You've got this block of superalloy, right? This is stuff made to survive inside a jet engine, and you're supposed to carve it with perfect, microscopic precision? How do you do that without totally wrecking the part, or the super expensive tool you're using? That's the puzzle we're going to unpack today.
Okay, so to even start answering that question, we need to get on the same page about a really important term. It's the key concept that controls this whole process. What exactly is machinability?
So, here's the textbook definition. It's all about how easy it is to cut a metal. But what does easy really mean here? Well, it boils down to three things. 1, you get a great surface finish on the final part. 2, your cutting tools last a long time. And 3, you're not using a crazy amount of energy to do it. Nailing all three of those at the same time? Well, that's the real trick.
Right, so how do engineers know if they're actually getting it right? How do you measure this stuff? Well, you can think of them as detectives, really. They're looking for clues. And the biggest, most important clue is something you can't even see. It's all about reading the forces. See, every single time a tool slices into metal, that metal is pushing back. It's resisting. And that resistance, that pushback force, tells you exactly how hard the material is to cut. It makes sense, right? Higher force means a tougher job. The challenge is you need some seriously sensitive gear to measure it. And that's where this thing comes in, a dynamometer. The easiest way to picture it is like an incredibly sensitive bathroom scale, but one that sits under the metal part while it's being machined. It measures the force of the cut from all different directions with crazy precision. What you get is this live, second-by-second readout of the epic battle happening between the cutting tool and the material. And look at what this data shows us. It's fascinating. For example, Guj and his team confirmed what you might expect. Change the cutting speed, or how fast you feed the tool, and the forces change right along with it. Makes sense. Then you've got Ozlu and his colleagues who found that the perfect, optimal cutting settings always happen when cutting forces are at their lowest. But this last one is wild. Huang's team tried adding ultrasonic vibrations to the tool, and get this, it dropped the cutting forces by more than 20%. That's huge. So the big takeaway is that these forces aren't set in stone. We can actually control them, and a lot. And it's not just about raw force. Sometimes the clue is a vibration. Yeah. Researchers like M.Com's team literally just stuck accelerometers, the same kind of thing that's in your phone, onto the cutting tools. And they found a direct link. As a tool gets older and more worn down, it starts to vibrate more. It's like a little warning bell that something's about to go wrong way before you could ever spot it with your own eyes. Okay, so we're measuring all these forces and vibrations. But why? What's the point? Well, it's not just for collecting data. It all has a very, very real impact on the end result, getting that perfect surface. And this, right here, is the name of the game, surface integrity. We're talking a surface that is flawlessly smooth and, just as importantly, free of stress. Because this isn't just about making things look shiny and nice. A bad surface on something like a turbine blade or a hip implant, that can literally cause tiny cracks to form and lead to total failure. So yeah, getting this right is a huge deal for safety. So how do you actually control that surface quality? Well, research from Zoe's team points to one of the biggest knobs you can turn, the feed rate. That's just how fast you're pushing the tool into the material. It's a simple trade-off, really. If you go fast, you get a rougher surface and you trap a lot of stress inside the metal. If you slow it down, you get that nice, smooth, stable part you're looking for. But check this out. Sometimes a tiny little tweak can have a massive impact. In 2023, Pang and their team were just experimenting with different cutting fluids. The liquid that gets sprayed on the tool to keep it cool. And they found one particular fluid, just by swapping it in, reduced the surface roughness by a staggering 20%. That is an absolutely incredible result from such a small change. All right, so we've covered the forces at play and the final surface quality. But there's a third piece of this puzzle, and it's a big one. It's all about the tool itself, its health, how long it lasts, basically a tool's life and death. Now, in the world of machining, the way they measure a tool's lifespan has a technical name, flank wear. But really, all it is a tiny flat spot that gets worn down on the side of the tool's cutting edge because of friction. Just from rubbing against the metal over and over. And once that little flat spot gets too big, that's it. The tool is officially done.
And this is pretty much the life story of every single cutting tool. It starts out brand new, perfectly sharp. Then it starts cutting, and that little bit of flank wear shows up. It just keeps getting bigger and bigger until, well, the tool either snaps or it starts making the surface finish look awful. The whole game is to pull that tool out and replace it right before that last stage. But how do you know when that is?
I mean, this is literally the million-dollar question in manufacturing. If you stop the machine and change the tool too soon, you're just throwing away money on a perfectly good tool. But if you wait too long, you could ruin a part that's worth thousands or even tens of thousands of dollars. You have to know the exact right moment. So how can you predict the future?
It turns out you do it by listening.
No, I'm serious. This is one of the coolest things I've read about. A team led by Sun is using these super sensitive microphones to listen to something called acoustic emissions. Basically, they're listening to the actual high-frequency sound of the metal being cut. And what they found is that the sound changes as the tool wears out. It follows a pattern, which means they can literally hear failure coming in real time.
Okay, let's step back for a second. We've got data on forces, on vibrations, on surface quality, and now even on the sound of the cut. So the big question is, what do you do with all of it? How does it all fit together? Well, the answer is what we call the smart factory.
It's crazy to think about, but the old way of doing things, and I mean not that long ago, was all manual. You had to physically stop the machine, pull the part out, get your calipers to measure it, maybe look at the tool under a microscope, then put it all back and press go. It was so slow, so inefficient, and it was all just based on a person's best guess.
Today, though, is a completely different story. Now machines are absolutely packed with sensors. They're measuring forces, temperatures, vibrations, everything, all at once. And all of that information is streaming, in real time, into a central brain.
And yeah, you guessed it. That brain is powered by AI. And it's changing everything. We're talking about machine learning models that can predict what the surface roughness will be before you even make the cut. There are cloud systems that let an engineer check on a tool's health from their phone miles away. We have AIs that can change the cutting parameters on the fly to react to what's happening. And of course, data-driven models that tell you the exact best time to swap out that tool. It's incredible.
And that really is the crucial point here. Understanding all these factors, the forces, the surfaces, the tool life, it isn't just some abstract science project. This is what lets us build the modern world. It's how we make everything from our phones to spaceships more efficiently, more precisely, and with a lot less waste. This is the science that literally builds the world around us.
Which kind of brings us to a pretty wild final thought. We've gone from a guy with a microscope to factories that can literally listen and feel and think. It really makes you wonder, right? If our factories are becoming this intelligent, what's the next impossible thing we're going to be able to build?